Hello everyone, let's start the tutorial for this week. We have two questions. Question 9 and question 10. So this time it's still based on the previous lecture about your given a process, how to use your process models and the measure data to get the link between the physical models and empirical models. Okay? So we'll see it and we can start. This is a video, so we can start this session. But let's see, you have seen the answers beforehand, so I guess you have seen the first case, still similar. We have the stirred tank heater in this example. So you can see the overall diagram. And we have the function to describe this process. So this week we won't repeat what we use the energy and the mass balance to get the equations and then do the Laplace transform, because we have done this before. So if you want further practices, you can get from the previous lectures. But in this case, we have this stirred tank heater with this figure. And it's used to preheat a reactant containing a suspended solid catalysis. So it becomes a real process. You use a heater to preheat a process. But still, when you do the modeling, it's not that important you see it's a catalytic reaction or it's a water heater. The energy and the mass balance still based on what you know about the process. You can derive the similar description for the process using the first principle models, and also get the measurement from the process. Right, so here we give that the constant flow rate is 1,200 kg per hour. We know the volume, the V, is given to 0.1 cubic meters, and density and specific heat of these mixtures of this liquid is given. Then if we know initially this process is operated with the inlet and outlet temperature to be 90 degrees C and 120 degrees C. So here we have the assumption that assuming no heat loss, what is a process model? So in this question statement, we already give you the transfer function. So we give you the function in the S domain here. But if we ask you to start from beginning, you should know you always start from your overall energy balance and then consider the accumulation equals energy in minus energy out. That is our overall energy balance we have used. And then we use the deviation variables to turn the time domain function to the Laplace domain to get the transfer function, because we always use this format. So you can practice how you can get from beginning to here. But one important point is that we have the term of no heat loss. So the heat loss is assumed to be zero. So what is the heat loss term in the energy balance? Right, so that's the term you consider generally. Normally we write this is. I said I won't write down for you, but I still keep writing the energy balance. Just like a practice, you should be able to write this yourself. And this is the energy heat loss. This capital heat loss is the exchange of the energy from the tank to the surrounding environment. So here we assume this term is zero. So that is important part. When you do modeling, read the question statement and say what is there and what you can assume to be zero. Make the assumptions before you go to the calculation. So it can simplify the process. Okay, so you can try the practice from here to the S function. Now here we just know we have this temperature equals K over S plus 1 So here we use the deviation form already, but we just write the overall transfer function. Because this is from the antibalance, you know the K and tau already. So K is 1 over WCP. And this can be calculated because in this case, you're giving the physical parameters. You know the W is the flow rate of 1200, and CP is given as well. So you're able to get the value. And tau, the time constant, the same way. Okay. So the first step, we are able to get the tau, K and tau. So what is out of the process then? If you see the transfer function, it really describes the outline temperature T relating to two of the input variable. One is the Q, which is the heating amount. The other is the Ti, the inline temperature. So this is what we use the transfer function to describe linking the output to input effect. Although they have two, you can add them together. The transfer function effects are addictive, so you can get the transfer function with respect to H. This is the first step. We understand the process from the description. And then based on this, the real question is asking you 3 step questions. What is, first of all, what is the heater input at the initial steady state? So this is a basic question. Even if you haven't taken this class, you'll know it. Initial state is a steady state. So if you want to calculate the heater input, you only need to use the temperature difference, use the physical properties. This is easy. We can directly know at the steady state, since there is no heat loss, so the heating effect all goes to the temperature change. Directly the Q, you add this Q amount to the reactor, to the heater, then this equals WCP T minus Ti to be the heating of the temperature of the fluid. Okay, so because here W is really our given at the mass flow rate, so we don't have to multiply the rho term. So this is the very beginning of the course. We know at steady state, just dynamic term is 0, so you can calculate the process or basic step. And next one, we ask you if the heater input is increased by 30%. How long will it take for the process to reach a new steady state output? So this becomes the dynamic. If I increase my heater amount to the 1.3 times of original Q, what is the time required for the new steady state? So now you are doing the project, you have to do simulations, so you're able to know if you can use the first order process, how is the time related to the between the two steady states. But when we go back to the original first order process, we know the first order response is always just like from the beginning, and then within certain time constants, you are able to reach 99% or 99.7% of the final state. That is regarded as a steady state already. So this 5 tau is from our analysis of the function. We know we can describe the response. Because we discussed from the model, it is a first order process. So we are able to use yt equals km multiplied by 1 minus e2 minus t over tau. It's a general first order response in the time space. So we have already got tau has 1.75 hour. So we are able to use 5 tau to indicate the time. Okay. Then if you want to get the final state, you can, from the figure, we know that this final state has a value of km. And so we already know the value for the km. We know that we know this final state. And km can be calculated. We know k is calculated already for system. It's a fixed constant. Steady state gain for the process, for the case. then M is your input because it's a step response. So M is a magnitude of your step change. So we know it's 30% of the heater input. So it's 30% of the value of Q. Because Q is known as well, so just use the whole calculation, very straightforward, to get the value for Km. Okay? Because now we already use the deviation variable, so we've got this value. Don't say this is directly the final temperature, because now we use deviation, so you should add this Km value to the initial steady state. We know it is 120. Because this is the outlier temperature. Initial steady state is 120. So add this 8.99 to the 120 to get the outlier temperature after step response. Okay, so just use the Km value to calculate this. And the next part, it asks you, so just now we calculate when Q changes, what is the corresponding T change. Here we switch to another variable in the transfer function. We say because the inlet temperature also has some variations. If my inlet temperature is increased suddenly from 90 to 110 degrees, so this is 20-degree change in the Ti, in the inlet temperature. Now how long will it take the outlet temperature to change from 120 to 125? Okay. So now it's not asking you to reach the final steady state, just ask you how long will it take to reach this 5-degree change. So it's use the change of the temperature, change of the magnitude back to at the time required. Again, it's using the same formulation, just solve the equation, and now you know that the magnitude to go back to solve for the time. So it's the same equation. Because we know this is the first order step response from our governing function. So we know that Yt over Km has this exponential relationship. And in this case, what is the K value here? Shall I use my K calculated initially? Alright, we got transfer function. So now we care about T and Ti. So we know that this is a transfer function I should use. So here, the K value actually is just unit, just 1, to describe this pair. So when you do project, you have different pairs, input, output pairs. Using these pairs to get different transfer function. So here this K, this new K, just 1. So when you do the calculation, pay attention to a detail here. Just use 1 as a gain, steady state gain for T and Pi pairs. Okay, so that's the only thing we need to pay attention to. The rest is just the normal calculation. Km 1 by 20, M is a 20 degrees C change. So we know the Yt is 5 degrees C change. All deviation variable. So when we use the 5 output divided by the Km value, we're able to solve for the temperature here. Because tau is the same tau for both transfer functions. So we can use the whole thing to calculate the time required. Okay, so this is relatively easy, just first order process. But if you've got different orders, different functions, you need to think about how to use the same procedure to use this response function, switching from time domain and S domain to calculate the time required to reach the final steady state or to reach certain operating state. Okay, this is question 9, not difficult. Then the next one is based on the process diagram again. So it's not describing the physical process. We directly start with the transfer functions. So we give you this block diagram to see I got input signal PS. If we have this model structure involving a second order process, here is the second order process, in parallel with the first order process. This is a parallel structure. When the signal PS passes through both processes, you got the RS top and the QS bottom, and sum them together to get the final output PM. Okay, so this is the block diagram. And we see this model can represent a Fleischer-Meyer device. So it doesn't matter what process. Here we just focus on the equations directly. So here we are given the data. We know that from the preliminary results, we know the first order process has a time constant of tau equals 20 and the gain of k equals -3. So we are giving the k and tau for the first order process. We can directly write the first order process here. You know it's just two parameters for first order process, k and tau. But we don't know the second order process. So our goal is to use the process data to estimate the second order process parameters. But luckily we got additional tests. So we have this input with a step change in peak from 2 to 4. So this, you know, is peak and input a step. So when you read the question statement, you better draw something, draw the diagram, or write down the conditions, what are given to you already. Write down these known conditions. So know this is your input P. And then this is the output response of PM over the time horizon. Okay. Then the question is to estimate the values of k, tau, and zeta, which are the three parameters for the second order process of k, that is the gain, tau, and constant, and the second order zeta parameter. How do we do this? So whenever we got data, you would like to find some pattern within the data. The best way is to visualize it. Always to plot the data and see what is the response. So you're able to see, even if it's not complex, using hand, you're able to see, plot the data and see the trend. Since we already know the second order, first order structure and the first order parameters, and the final output of PM, you can think about when you get the parallel structure connecting one first order and one second order, those effects can be added together. So the first order process normally just got in the time domain just got converted to a final steady state. But for second order, sometimes has more dynamics. You got the overshoot and can have the periodical response. So these are typical second order process. So for overdamped or underdamped, you can think about these terms we discussed in the lecture. The second order process, it has different response types. But this is the type of the addictive effects we got from the data. Because we know, so this is governing, we know that P is an addictive effect of R plus Q. So we should do them separately to see what is individual effect first. Okay, so the input is just a step response with a magnitude of 2. So definitely PS is 2 over S. To write in time domain, just a step function translated to the S domain. And then we use the input first acting on the first order process. Straightforward, just write the transfer function, write the input, and it got the output from the bottom is QS. And in the S domain again, we want to compare the effect on the time domain. So you should now be able to flexibly transform them from Laplace domain to the time domain. Use Laplace inverse Laplace transform. You got the Q and P in this format. Note that here we use Q prime as a deviation variable in the time domain. When we do a Laplace transform, it's a deviation already. Okay. So since we know the QP, we know the PM, then we turn the PM as to the time domain as well. So here, by definition, the deviation of PM prime is just use the real PM output in the time domain minus the initial value of PM. So PM0, the initial steady state value. We always assume the system starts from the steady state at the time 0 as the initial. So this is actually PM bar, right? PM0 same as PM bar when we write in the deviation format. Okay, and this PM prime equals R prime plus Q prime, all in deviation form. It's just from the system structure. Okay, we know this. And then compare this with the known data. We want to substitute as much information as possible. So if you have a look of the data, then we know the PM0, because it's PM ID time minus the PM initial condition, is what is from the given table. You're able to read initial PM is 12. So this is initial condition. It's used, you can directly use this 12 as an initial condition. This PM0 is 12. And since we already know Q prime is from the first order response, so we can write this part as minus 6 multiplied by 1 over exponential term. So we can directly use this term here, so minus Q prime, we are able to write this in. So now we got a nice condition, because we just get the relationship between the R and the PM. So we're able to use the PM data to further get the insights of the R. Okay? So now we have this, we try to think about what does the parameter mean for individually for K, tau, and zeta, those terms in the second order process. And then use the definition or use this empirical formulation to calculate their values. So first of all, for K, we are familiar with that. We use that in first order, second order. We call it the statistic gain. So what does K mean? If you think further, you can use different ways to consider it. So when you have this in a time domain, we'll go to the final steady state. We call K the steady state gain. So by its definition, it really means the whole how the output change relating to the input change to get the gain value at the steady state. So it really goes to a steady state. So one way, if you understand in this way, then you can calculate using the final value of the output divided by your input to get the value. So this is one way, because for the second order process, your output is R, your input is P. So use your output at the final value. When it goes to steady state, divide your input of P. You can also think about the case meaning using the final value theorem. So it's directly we can see, because at the final, when time goes to infinity at the final value, it means the value is equal to s goes to 0. So when even first order or second order, when s equals 0, the whole thing becomes just k itself. So the value is just k. And also describes the k means that it's the final value using the output. Describes when you how much you amplify the system to get the output. So both ways can help you understand what that's meaning. So now we know the final value for R prime can be calculated from this expression. So we're able to know it's just substitute the final value for PM. Because here from the data, when the time goes to several steps, when it reaches steady state, you can use the 18 value here. PM equals to 18 as the final value. So this gives you the final value at equals to infinity. This term is 0 as well. And we also know that P value is a step response. So the change is 2. So directly we are able to calculate the value for K. It's 6. That's for K. And then we need to know the other parameters. So because this, we ask you what is the system, second order system. Because of this response type, we know it's underdamped process. For underdamped process, we have the overshoot, we have the period to describe the process. And this is from the book. We directly know. We didn't talk much about this in the lecture, but these are in the books. You can directly use this equation to describe the second order process. What is the time to the first peak? What is the overshoot? What is the decay ratio? And the period. So these are typical characteristics to describe the process can be obtained from the value of zeta tau. Okay. So now our task is just to read this value from the figure and then use them back to calculate the tau value. So since we know the overshoot is just what's the definition of overshoot? Think about it. You have the figure and then you use a figure to calculate the overshoot. What's the definition of that? So this is a percentage or portion fraction of the peak value, deviation from the peak value to the steady state to a final value divided by the final value. So because here we focus on the second order process, so we need to read the R. So we again use R equals P minus 12 plus this exponential term to get the R's value. So we know the peak is happening at, again, read from data, this is the first peak. So we use the PM15 to get the value, calculate the R. Why can we directly use the P to calculate the R? So here is another thing you need to state, because it's an additive effect of the first order process plus the second order. And we know that for the first order process, it's like a monotonically decreasing process or increasing process. So the trend is a simple trend, it's a modal trend. Therefore, we will sum this first order plus the second order. The final PM also shows that the period of the whole shape of the curve will be similar to the second order one. Therefore, we are able to analyze the data from the final output to get insights for second order process. Okay. So we already used the overshoot value directly there because overshoot is giving us the corresponding value of zeta of this parameter. So we calculate the zeta here, and we know the period for the R is the same as the period for the final PM. So we can read the period from the figure again. So if we don't draw it, it may be difficult, but when you see this, you just read the two peak values. The first one is 15, and read the second peak is 50. So you know the period is 35. This is your period value, and we can use this function that we know zeta already, so we're able to calculate the tau value. This question really gives us understanding of how to use the second order process. So here we give you the underdamped process to see the oscillations and read from the figure, use the values to calculate the parameters of the system. It's clear? So this time the questions are not difficult, but you can practice the calculation. Just be careful about the calculation and examine your results.